Sorry, this is the last talk of the day, so you're probably tired. I'll try to keep it under an hour if I can. So, while everyone's coming in, I thought I'd have this slide on the screen. And this talk is about domain modeling and how the kind of type system in a functional language like F# or Haskell can do a kind of domain modeling that's different. And so I thought I'd put up a little quiz at the beginning. How many things are wrong with this design? So this is how you do a kind of a record type in F#. You can see it sort of looks a little bit like JSON. And I'm going to ask you how many things are wrong with this. And we will, through this talk, we'll go through and fix them. So, but before we get started on that, let's just talk about process. So if you think of the software development process like a pipeline, there's an input and you do something, and then there's output. And we normally focus on the software development side of things. We talk about compilers and tooling and testing and blah, 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 because that's what we care about. But just like any kind of process, if you have garbage in, you get garbage out. So no matter how good your coding is, if you have bad requirements or unclear requirements, you're going to have a bad product. So this talk is really going to focus on the requirement side. What is the input to our development process, the design phase? Trying to understand the requirements, trying to document the requirements. If we can have good requirements, then there's a hope, at least, that we'll have a decent product. So this is the design, and that's really the focus of this talk. Okay, so let's go back to the challenge I gave you before. The first thing from this thing is it's not very clear which things are optional. Strings could be null or something. Is the first name optional? Is the middle initial optional? Is the last name optional? Some of them are required, some of them are optional. It's not at all clear from this design, right? So that's a problem. In terms of documentation, you might have tests in the code. You might have a piece of code that says, yeah, well, this has to be a non-null or non-empty before it's allowed. But that's in the code. I'm talking about in the design, in this design here that we're looking at. So in this case, the middle initial is optional and the other fields are required. It's not at all clear. So we're going to try and change our design to fix that. What about the constraints? Can the strings be infinitely long, or can they be 32 bits long or 64 bits long, however long a string is, a couple of gig? Can they contain non-printable characters? Can they contain line feeds? There's probably some constraints on the string, right? Especially if you have to actually print it out on a mailing label or on an envelope or something, or you put it in a database. For example, here we have a constraint: the string can't be more than 50 characters. And again, you might have some validation rule somewhere, but that's not in the design. I have to go and try and find out which piece of code has this validation rule and try and fix it. What about which fields are linked? So if we have many people using the system and somebody updates the first name and somebody updates the last name in two different devices, is that an error? What happens if one person updates the name and the other person updates the email at the same time? Is that an error? Well, in this case, the name fields are linked and the email fields are linked. They have to be updated at the same time atomically. But they could be separate. You could have one person update the email, another person update the name, and that's fine. And that's not clear from this design either. And finally, what's the domain logic? We have this flag here. Is email verified? And this is set when you put in an email address and you send you back a link, and you have to click the link to prove that you own that email. When is that flag set? Right? Under what circumstances is it set? It's just a Boolean. It conveys absolutely nothing right now. Again, you have to read the documentation to find out. So that's a really bad design. Let's see if we can improve this design as well. So in this particular case, the logic says if you change the email, you have to reset it to false because I need to send you another verification message. All right, so which values are optional? What are the constraints? Which fields are linked? And what's the domain logic? F# is great for all this stuff. And I think by the end of the talk, you'll see what I mean. So domain modeling made function, that's this talk. My name's Scott Wlaschin. I have a website, fsharpforfunandprofit.com, so obviously I'm a little biased towards F#. But these techniques will actually work with any type system like this, so OCaml or Haskell, maybe even Scala. So a lot of the ideas in this talk come from the Domain-Driven Design book. If you haven't read it, I highly recommend it. But the main point of this book is you focus on the domain rather than technology. Okay, I don't care about the database. I don't care about the web browser. I care about what is the business domain. What do people actually care about when they do their jobs? That's normally considered sort of OO thing, but I like to do it in a functional way. So this is a kind of intersection of the functional programming people and the domain modeling people, and we're sort of right in the middle here. So I'm going to demystify functional programming because a lot of people are scared by functional programming. So I always stick this at the beginning of my talks. I think I won't have to in a few years, but for now I will. So if you're not scared of functional programming, that's great. I'm going to talk about functional programming for real-world applications, because a lot of people think it's sort of an academic thing. And then I'm going to talk about what is the F# type system and why is it different from an object-oriented model of classes. And then we'll actually dive into the meat of it and actually design this domain using the types. So functional programming sounds very scary because there's all these words, functor and catamorphism and currying and monoids and the dreaded monad. And you look at all these words and it's like, oh my God, they're awful. You know, it's way too scary. Here's Homer being very scared. Now, I think it's actually not that scary, but it's unfamiliar. These are words that you don't know what they mean, but doesn't mean you couldn't know what they mean. And one of the problems is that the words tend to be kind of mathematical. If you rename the words to something like, instead of a functor, it's a mappable, instead of a catamorphism, it's a collapsible or something, an aggregatable, a chainable. These words would sound less scary. You still wouldn't know what they mean. I mean, here's Homer. He's still kind of puzzled, but it's not. It's now just something you just need to learn. It's not something so scary that I'm going to give up completely. So just be aware that the concepts are actually not that hard. It's just the words can be off-putting. I'll tell you what's really scary is object-oriented programming. Object-oriented programming has all these really scary words like polymorphism and inheritance and interface, generics and covariance and solid. And solid has 5 other things inside it, and IOC and DI and ABC and MVC. And so what makes you think that functional programming is bad, right? Object-oriented programming is way scarier than functional programming. There's all these things you have to know, all these strange terminology that you have to understand, right? This is not scary to you because you probably know all this stuff. So I guess this is my point is, if you know it, it seems quite sensible, and if you don't know it, it seems scary. So please don't be put off by the terminology. So the thing in this talk is we actually don't need any of this stuff in this talk. We're not going to be doing any of this stuff. No monads in this talk. It's a monad-free talk. We're going to be talking about everything else other than monads. All right, so that's my little rant on please don't be scared. Let's talk about real-world applications. So a lot of people heard that functional programming is good for mathematical stuff, and it's good for algorithms, and it's good for parallel processing. But you need a PhD to understand it, right? Well, it's true that it is good for mathematical stuff, and it's good for algorithms and so on. But it's not true that you need a PhD. You can, it's like I say, it's actually really simple once you get the hang of it. So what I think functional programming is really good for is boring line of business applications, okay, which I call blobbers. So this is what most of us do in our day job, probably. It's enterprise software, it's accountants, it's inventory management, fulfillment, e-commerce websites, I don't know. But it's pretty boring. I mean, mostly. It's not exactly the most exciting stuff. But if you think about blobber development, there's some things that you really need. You need to express requirements clearly because you're trying to communicate with people who are clueless. You need a rapid development cycle because you want to get the stuff out there before the customer changes their mind. You want high-quality deliverables because you don't want to have to go back and fix a bug from 6 months ago when you're swamped with stuff today. Right? So these are very important things. And what's interesting is that these are the same principles that the Agile movement has, and they also came from blobber development. They came from a payroll system, I think, originally. So F# is really good for this. It's very concise. It's really easy to express requirements clearly, and we'll talk about that today. It's a rapid development cycle, because not only can you do all the unit tests and stuff, but you have an interactive environment you can do stuff. And it's high quality deliverables, and we'll talk about how we can bake quality into the design, so we can avoid even writing unit tests. And of course, the most important thing is fun, because if you're going to be writing boring business applications, at least you can have fun doing it, okay? And as it happens, fun is a key word in F#. So there you go. All right, so here is a cat and a dog, and this is like functional programming and blobber development. Very happy together. All right, so domain-driven design. So for people who aren't familiar with domain-driven design, I'll just quickly go over some of the kind of key points. But the most important about domain-driven design is about communication. It's about you have a model of what you think is happening, and the domain experts have a model, and often the model is different. And so the point of domain-driven design is to get your model and the domain expert to share the same model. Right? You basically are working on the same shared mental model. Because remember, it's your model that goes into production. Right? And if your model is wrong, the system will not do what it's supposed to do, and the domain experts will get angry at you. So if you can try and communicate, if you can try and get a shared model going, that's great. The only way to get a shared model is to have really good communication. So let's look at communication. So what is this word? Unionize. Okay. So some people might think it's unionize, right? Power to the people. And other people, especially if you're a chemist, might think it's unionize. Okay? So which one is it? Which one is it? Well, the answer is it's both, of course. It depends on the context. So this is the first point about domain-driven design, is there's a context for everything. In business, unionize means one thing, and in the chemistry context, it means unionize. So we have to be very careful about thinking that the other person understands what we're saying, because there might be different words. Here's another one, spam. Okay, in a supermarket, spam means canned meat. In an email system, spam means junk mail. Right? So in the different contexts, the same word means something different. But okay, that's really obvious. What about product? Okay, this is where it starts getting painful, because in one business, the sales team might think of a product as something you can sell. In the warehouse management team, they think of product as something that's physically in the warehouse. And stuff that you can sell might not be the same thing as in the warehouse. They might be slightly different. So there's a potential for confusion here. What about customer? There's another one. Sometimes you see businesses where they try and create a domain model that stretches over the entire enterprise, and everyone is supposed to use the same words. That's doomed to failure, because different parts of the business use the same word to mean different things. So in marketing, a customer means somebody you can send an email to, somebody you can spam. In the finance world, the finance department is somebody who owes you money. That's what a customer is. So again, different definitions of what a customer is. And the best way, rather than trying to have a generic customer that matches everybody's thing, you divide the business world or the domain into little chunks, which is called a context, a bounded context, and you work inside those chunks. Now, within those chunks, the word means the same to everybody. But when you cross the boundaries of these chunks, when you go outside your world and go into somebody else's world, it's quite possible the word means something different. So another important concept in domain-driven design is the concept of a ubiquitous language. So a ubiquitous language is the language you use in the shared mental model. So when I say customer and you say customer, we're talking about the same thing, and we need a language to communicate. Let's all use the same language. Okay? So in chemistry, here is the ubiquitous language. For chemistry, you might have a polymer. Now, it's very important that we don't talk techie. We don't say a linked list of molecules or something. We use the word that the domain experts use, which is like a polymer. We don't say a linked list, even though we may implement that in our code. It's very important that the code uses these terms, the same terminology, so that when I look at the code, I see the domain model. And we call this the ubiquitous language. And of course, every domain has their own ubiquitous language. So in sales, you might have a product and a customer and a tracking. And again, in a different domain, same in another set of ubiquitous language. Some of the words are the same, but they mean something different because it's a different context. So here's some code. Let's look at actually how you do this. Can you guess what this code is? What kind of domain are we talking about here? Any ideas? Well, first of all, you can see I've got a clue up there. It's a card game. Now, you might think, well, it's obviously a card game. But for example, if I didn't say it was a card game, then the word suits could be something to do with clothing, right? And maybe the word hand was something to do with, medicine or doctors or something, I don't know. But the fact that there's a card game context, then these words make sense within the card game context. So that's the bounded context. And then this is the ubiquitous language down the side. All these are the nouns and the verbs that you use in that context. So this is F# code. So let me explain it to you quickly. So the vertical bar means a choice. So a suit is a club or a diamond or a spade or a heart. A rank is a 2 or a 3 or up to an ace. A card is a pair, so that little thing means a pair, and we'll see why we use multiplication to mean a pair. So a card is a pair of a suit and a rank. A hand is a list of cards. A deck is a list of cards. A player is a name plus a hand. And a game is a deck plus a list of players. The list type is built into F#, it's very nice. And here's a verb. So when you see this arrow in F#, that means it's a function. So this is a function where the input, the thing on the left-hand side, is a deck, and the output, the thing on the right-hand side, is a deck and a card, a pair. So I can read this and say, well, the input is a deck. The output, when I deal, is a new deck because the deck is going to be immutable, and there's also going to be a card on the table. So that's what the output is. And when I pick up a card from the table, the input is my hand and the card on the table. That's the input, a pair. And the output is my new hand, and the card on the table has disappeared. So this is a documentation of the nouns involved and the verbs involved. So here's a question. Do you think this is a reasonable amount of code to write to document this domain? Basically a page of code. I would say, yeah, not bad. I've got 9 different things on one slide. Pretty good. Do you think a non-programmer could understand this? If I was showing it to somebody, I say, I'm not sure, is a diamond one of the suits or something? They could correct me and say, yes, it is, or no, it isn't, or whatever. If I've missed something, they could probably check it. One of the things about this model is it's what we call persistence ignorant. There's nothing about databases. There's nothing about foreign keys. There's nothing about primary keys. There's nothing about tables. There's nothing about classes. There's nothing about inheritance. There's nothing about interfaces. There's nothing except the domain. This is purely all about the domain. This is why it's called domain-driven design. It's not called object-oriented design. It's not called database-driven design. Domain-driven design. The whole point is to focus on what's important in the domain, and everything else is irrelevant right now. So what's interesting is the design. This is a design, and it's also compilable code. One of the goals of agile development, is to make the code be the design, because if you have the design in a separate UML diagram or a separate document, it's always going to get out of sync. So if you can keep the design and the code in sync, that's fantastic. And the best way to keep the design and the code in sync is to have the design in the code. So I think this is a great example of how you can do this. So this is not pseudocode, this is executable code. You could stick this as the first file in your F# project, and it will kind of define the domain for the rest of the project. So we don't need any stinking UML diagrams in our F# driven design here. All right, so that's the basics of domain-driven design, the kind of the key ideas. So let's look at the F# type system and see why I think it's really good for doing this. The F# type system is what they call an algebraic type system. Algebra, just like x's and y's and adding and multiplying things. We'll see. It's a kind of mathematical word. So I actually prefer composable. So composable means you can glue things together like Lego, and you can build bigger things from smaller things. So there you go. There's some Lego. Right. So in the F# type system, well, first of all, F# types are not classes. They're just data structures. So they don't have any behavior. which means it's really easy to glue them together because you don't have to worry about what is the behavior of them when they're glued together. That's a different problem. So to create a new type, you can just glue them together in two different ways. You can multiply them together, and you can add them together. Okay, now that sounds a bit weird. It's like, how can you multiply a type? How can you add a type? What does it even mean? So let's look at what this means. Okay, so here's a function, and we're going to use the classic thing as a function. It's a little box, and there's an input and there's an output. So for example, the add1 function, the input is a list of numbers. The input is one of the integers from the list of integers, and the output is another one of the integers from the list of integers. Okay? And in F#, we write this as an int, arrow int, meaning int is the input and int is the output, with the arrow telling you that it's a function. So that's how there's a set of integers which could be the possible inputs. What happens if the input is a pair? Let's say we want to add a pair of numbers together. And the output, we can say, well, that's an integer. But what is the input? How can we define what the input type is? In object-oriented, we'd define a pair class. We're not going to do that. We're going to build a class. We're going to build a type by composing existing types. Right, so let's have a look at this. If you think about it, a pair means that you have a pile. You take one from the first pile and one from the second pile, right? So if there are 4 things in the first pile and there are 4 things in the second pile, how many possible pairs are there altogether? 16, yes. 4 times 4. There's 16 possible combinations. All right? So this is where the multiplication comes in, okay? What about if you have a pair of booleans, okay? So there's 2 possible booleans in the first pile, 2 possible booleans in the second pile. How many possible pairs are there? There's 4 possible pairs. It's 2 times 2. So we call this, we call them like multiplying the types. So a pair of ints is written as int times int, and a pair of booleans is written as bool times bool. Okay, so that's why we use the multiplication. And we call these kinds of things product types. Product types. So here's an example. You say, okay, well, that's very theoretical. Let's look at a real example. Let's say we want to model people's birthdays. Okay, so what is a birthday? Well, a birthday is a person and a date. A particular person and a particular date. That makes somebody's birthday. So we're going to say, well, there's all the possible people and all the possible dates, and the combination, you multiply them together, it gives you all the possible birthdays. All right, so we're just going to say a birthday is a person times a date. So that's our type. We've created a new type that we can actually use in our code that represents it. All right, so that's the multiplication. And I also said you can add types together. What does that mean? So let's say we have a function that tells you whether you have a fever or not. So we're going to pass in your temperature, and it's going to return a Boolean, true or false. But the problem is the temperature in Fahrenheit or is it in Celsius? Well, we want to design our function so that it works with both of them. So the input is a Fahrenheit or a Celsius. How can we model that? Well, let's say that there are 4 possible Fahrenheit temperatures. Obviously, there are more than that. And let's say there are 4 possible Celsius temperatures. How many possible inputs are there? 8. Thank you. There's 8. There's 4 possible from this. There's 4 from this pile, or 4 from this pile. So there's 8 possible combinations, and that's why we call it an addition, right? Because it's this pile plus this pile. Now, in this case, they might both be integers or something. So we need to distinguish between the Fahrenheit cases and the Celsius cases. So when we write our code, we're going to have to tag them, saying, well, this is the Fahrenheit case, this is the Celsius case. And we write it like this. We say the temperature type is a choice between an F, where there's an int associated with it, or a C, where there's a float associated with it. So that's how we would write a choice type, or a sum type. Okay, it's a choice between these two things. And this is the kind of type that you don't have in C#. This is very unique to sort of functional programming. So choice types are really, really useful for domain modeling. I mean, here is a payment method, and it says, okay, this is a cash. There's a choice. There's 3 choices. You can take cash, you can take a check, or you can take a credit card. If you take cash, there's no other information associated with it. If you take a check, there's a check number. If you take a credit card, there's a pair, and the pair is a card type and a card number. So in this one type, we've actually got quite a lot of domain knowledge, very compactly written. Does it make sense, yeah? So there we go, check number. And so what's nice is each choice can have its own set of data associated with it. Now, once we've got one of these choice types, how do we actually work with it? And this is where the concept called pattern matching comes in. So let's say we have a payment method. If we want to print it, the way it works is we basically deconstruct it in the same way that it was constructed. So we have to have a case. There's 3 possible cases in the data type, so we have to have 3 possible choices when we analyze it. So we do this match. It's like we're going to do a pattern match, and there are 3 possible cases. The first case is it's cash, the second case is it's a check, and the third case is it's a card. And what's interesting is when it does the deconstruction, it also extracts the associated data. So you don't have to like find out, like, you know, you don't have to say, is it this kind of class? And then if it's this kind of class, cast it to a class and then extract the data. It does it all in one step. Very nice. So if you think about the object-oriented version of this, let's say I wanted to implement this kind of payment method in OO, what I'd probably have to do is create a base class or an interface or something, and then I have to create 3 separate subclasses that implement that payment method. That's fine, but it's kind of annoying because this interface, there's nothing in there. There's no common behavior. It's just data. So this would be like a methodless interface, a marker interface, which is always kind of a bit of an anti-pattern. And the other problem is that if you're doing C#, you probably have a different file for each of these things. So your code is sort of scattered all around, and your data modeling code is kind of mixed in with your implementation code, which is kind of annoying. If you wanted to find out all the methods, you'd have to look at all the different files. And most importantly, I think, is that this is, with inheritance, it's an open set of choices, right? Anything that implements iPayment method is valid. So, for example, if I create a thing called evil and it implements iPayment method, that would be fine. Now, sometimes that is useful to be able to extend a thing, but often in business modeling, you actually want a restricted set of cases. It's like, I only accept these 3 payment methods. I can't just add another payment method without like changing quite a lot of stuff in the business. It's not just as simple as inheriting from something and implementing. This tends to be more complicated than that. So if you go to the F# model, what's nice is that all the choices are in one place, and it's a closed set of options. It's you know exactly, it's only these 3 choices. And the extra data for each choice is right there in your face. You don't have to like search around in different files. It's right there. So from a modeling point of view, this kind of approach is very, very nice. So if you think about types in most programming languages, we think of types as sort of an annotation that helps you type check. You make sure this is an integer, it's not a string, it's not a Boolean. So we think of it as just something that helps the compiler, stay accurate. But what we're doing here is we're using types as a domain modeling tool. So when we say that we're dealing is a deck and all the inputs and the outputs and stuff, this is not about type checking. This is about modeling your domain. So we're using types for 2 things. And what's cool is that in a language like F#, you can get both at once. You get the type checking and you also get the domain modeling, which means that the type checker, the compiler, can check your domain logic for you. Okay, so if you have a good static type system, it's almost like having compile time unit tests. You literally will not be able to write code that doesn't match the domain model. You don't have to write a unit test to test something because it literally won't compile if it's wrong, and we'll see an example of that shortly. So type all the things. It's all very good. All right, so there's the type system. Now let's take it out for a spin. Let's see what can we do with it. So the first thing is we talked about we want to have some sort of optional values, right? We want to say something's optional. We don't want it to be, we want to make it very clear that it's optional. So how can we do that? So here's our personal name, and the middle one is optional. So how do we represent optional values? Well, let's kind of go back to the beginning. Let's say that we have a length function that takes a string as input and spits out an int as output, right? So the input is a list of possible strings. Now, one of the problems in most type systems is that null is a valid string, okay? Null is in the list of things that you can pass into this function. And that's a problem, because null is not a string. You can't set phases to null, it just doesn't make any sense. So this null is really bad. Having null as a valid value for a string is really bad, because it's not really a string. It's pretending to be a string, but when you actually use it, it will blow up in your face. The compiler won't catch it. The compiler says, yeah, sure, null's a string, no problem. And then when you try and access the length of the string, it's going to crash. So I like to say that null is sort of the Saruman of static typing. It's going to pretends to be your friend, is going to stab you in the back when you're not looking. So nulls are really bad. So in the functional languages, nulls are not allowed to be part of the valid set of values. Okay, so we can't model an optional thing by saying, yeah, we'll just use null to mean it's missing. What we really want to do is model it using what we described. You want to say, well, it's either a valid string or it's missing. Okay, how can we model that in a type system? Well, I think we've seen this. It's either one of these things or it's one of these other things. So we model it as a choice. It's either a string or it's a nothing. All right, so it's a plus, so it's a sum type. So we're going to tag the top one with some string, and we're going to tag the bottom one with nothing. And then we can define a type like this. It's optional string. It's either something, and there's a string associated with it, or it's nothing. All right, so this is how we would model an optional string using our very cool type system. All right, this is awesome. And we get very excited by this, and we say, yeah, optional string's fantastic. And then actually, we also need an optional integer. Oh yeah, we need an optional Boolean. And I think you can see there's something wrong with this because there's quite a lot of duplicate code. So this is where we say, okay, let's not rewrite this over and over for every possible type. Let's make a generic version. Okay, and here's the generic version, and it's called option. It's a built-in type in F#. You don't have to define it. And that little tick T is F# way of saying it's a generic. So in C# it doesn't have the tick, and in F# it does have a tick. So that's a generic type. And then we can say, okay, so the middle initial is not just a string, it's an option of a string. And one of the nice things in F# is you can actually put it backwards. You can say it's a string option. So this looks very nice. I think if I say the first one's a string, the second one's an optional string, and the third one's a string, that's a nice design, and it's captured the intent of which ones are required. And in F#, if it's not optional, it's required. That's basically our rule of thumb. All right, another kind of thing we can do is what I call single choice types. So a single choice type is one of these choice types, except there's only one choice, right? So if here's an email, and there's only one choice of email. Here's another one, customer ID, and there's only one choice of customer ID. Why would you do something as silly as only having one choice, right? Well, if you think about it, an email address isn't a string, it's a wrapper for a string, right? It may be represented as a string behind the scene, but an email address is not a string because there's constraints around it. It has to have an @, and it has to be less than 100 characters, and and so on. So it's not just a normal string. A custom ID is not an integer. It might be represented by an integer in your database, but it's not an integer. You can't add 5 to a custom ID. You can't take the square root of a custom ID. It just doesn't make any sense. So these things are not. You have to make a distinction between what it is from the domain point of view and what it is from the representation point of view. And what we want to do is represent, there's a thing called an email address in the domain, there's a thing called a customer ID, and they are distinct. The fact that there's a representation behind the scenes is not relevant to the domain model. So what we do is something like this. An email address is an email address. It wraps a string, but it's not a string. A phone number wraps a string, but it's not a string. And as soon as we do this, we now have distinct types. So an email address and a phone number are now different types, and they cannot be mixed up. You can't accidentally pass a phone number to an email address. Okay, even though they're strings behind the scenes, they're now completely different types. And of course, you can do this in object. You could create a special object that contains a value. It's different. And for example, a custom ID and an order ID, they're different types, right? You shouldn't mix up an order ID and a custom ID. That could be really bad. So doing these single choice types allow us to do that. So let's create the email address. So we pass in a string, and we have some horrible regex that checks whether it's got an @ sign in it or whatever. So if it does match the regex, we're going to wrap that string in the email address and return it. And if it doesn't match the regex, what are we going to do? We're going to throw an exception. We're going to return null. No, we can't do that. What we need to do is say, okay, you gave me a string that I can't handle. I have to give you nothing back. So what we have to do is make a distinction between something and nothing. So rather than just giving you the email address back, I'm going to give you some email address back, and if it doesn't work, I'm going to give you nothing back. So if you look at the type signature, the original one said, you give me a string and I'll give you back an email address. And it's like, no. You give me a string and I might give you back an email address. I'll optionally give you back an email address if you give me a good string. And if you don't give me a good string, I'll give you nothing back. So now what we've done is it's now in the code is documenting the fact that it might not always work. Okay, so rather than just throwing an exception, I don't have to read the documentation. I can just look at this and says, yeah, you know, it might not work. There's some validation going on. Another very useful type is a constrained string. Like we have, you know, a string that has to be 50 characters or less, and we do the same thing. It's like if the length is 50, it's good, and if the length is not 50, it is longer than 50 or something, it's bad. So again, if we look at the signature, you give me a string, and I might give you back a string 50, or I might not. So you have to handle that. But in F#, these things are immutable. So once you have got a string 50, or once you've got an email address, you never have to check it ever again. Nobody can change it after it's been created. So you never have to do any kind of defensive programming. The initial thing of like when you've loaded it from the database or you're parsing the JSON file, whatever, you have to do this checking. But after that, you never have to check whether it's null. You never have to check whether it's valid. You never have to check is it going to fit in the database because the string's too long. So the defensive programming sort of goes away. Once you've done the initial kind of validation at the edges of your app, there's a lot less code you have to write inside the app. Here's another good one. This is a website, and you can order 999,999 things. That's a problem. That's probably a bug. Why is it a bug? Because the person writing the website probably used an int as their quantity, right? So that's not right. How can we stop people using an int? Well, we say, okay, we're not going to use an int. We're going to use a special type called an order line quantity. It's different from an int. It's a domain-specific type. It's just for this particular domain. An order line has a special thing. It's not a normal int. Again, you can't multiply it by 5 and stuff. So we're creating a new type just to represent one thing in the domain, okay? And how many people ever do this? How often do you write a new class just to represent a little thing like an integer? A lot of times we can't be bothered because it's too much work. And then one of these days we have a bug because we have a negative number in our order quantity or something. This one, you can never have a bug, because let's say we can do the validation when we create it, and if it is valid, it's a new one, and if it's not valid, it's a bad one. So, again, once we've got this order line quantity, it's immutable, it can never change, and it can never be bad. We never have to check it ever again. All right, so let's revisit the challenge. We had our original contact. So the first thing we did is we created a way of making optional stuff really visible to us. It's a different type. The second thing is we now have special types for each of these fields to make it very clear. It's not just a normal string, it's a 50-character string. It's not just a string, it's an email address. Okay, by creating special types, this is now more self-documenting. And it's also more self-validating too. The other thing is we talked about is keeping them separate. Well, of course, it's really easy. We just create 2 separate types. Each one is an atomic thing, and then we can create a new contact which has the name and the email contact info. So we've now made it very clear that these are separate atomic things, and we can now pass this in. When we persist these things, we can say, well, I want to save the personal name, I want to save the email contact info. Those will be separate transactions in the database, so we don't have to worry about them colliding. All right, there's one thing we forgot about, which is this email verified flag. So let's have a look at that in more detail. there's some rules around this, okay? If the email has changed, we have to reset it to false, okay? And we should have a rule that we can only set the verified flag by a special verification service. Because when we verify, you click the link and there's some kind of hash code, you check the hash code matches the email, and if that's all good, we've got a verified email. We want to make sure that that rule is followed. We don't want anyone just verifying it, because that could open us up. It could be a security issue. If I could hack into the system and change the email verified flag, then I could send myself a password reset message, to the wrong email address and so on. So it's really bad. We really want these rules to be followed. As it stands now, the design does not communicate these rules. So can we embed these rules in the design? Okay, not in some documentation, not in some piece of code that checks validation, something. Literally in the design. So that's the next challenge. All right, so right now, anyone can set this true. There's nothing, it's just asking for trouble. All right, so what we're going to do is create a new type. And one of the rules in domain modeling in F# is there's no problem that can't be solved by wrapping it in another type, okay? So we have our email address type, and we're going to wrap it in another type called a verified email, all right? So we're going to create yet another type. And now we're going to have our verification service. And the verification service, for its input, it takes a normal email address, and it takes some sort of hash, and it spits out a verified email, or maybe not, because maybe the verification hash doesn't match. So it's very clear that this is returning, you give me an email address, I might give you back a verified email. This is now very clear. You can tell straight away from this that it might not work. You don't have to look and see, does it throw an exception or something. And then what we also do is make this verified email type a private constructor, so that the only person who can create it is the verification service. So that's just like any kind of thing. You can just make it a private sort of type. And then now we go back. Now we've got this thing. We go back to our original thing, and we say, rather than saying there's a flag, we say it's a choice. So it's either an unverified email address or it's a verified email address. Okay. So there's a choice of two things. And what's cool is that in order to use the unverified choice, all we need is a regular old email address. And I can create an email address, that's fine. But to create the verified choice, I'm going to need a verified email. Where can I get a verified email from? Well, I can't create it myself because it's private. The only way I can get a verified email is from the verification service, because it's the only one who has permission to create it. So by doing this, I have actually embedded those business rules right in the design. Okay, I've guaranteed, I don't have to write a unit test for this anymore, because the code, the design encapsulate those rules. And not only does that, it also, looks nice. Okay, we'll see in a minute. So here's our completed challenge. Email address, we've got all these new types. Before we had one type, and now we've got email address, we've got a verified email, we've got an email contact info, we've got a personal name, we've got a contact, we've got string 50, and all these other things. So let's go back and visit the challenge. Which values are optional? What are the constraints? Which fields are linked? And what's the domain logic? So we can clearly see which values are optional because they've got an option next to it. Okay, that's right in my face. I don't have to go and read the documentation. What are the constraints? Well, it's really obvious. This is a 50-character string. This is a 1-character string, and so on. Again, I don't have to read the documentation. I don't have to dive into the code looking for validation rules or anything. Which fields are linked? We've now broken the original thing into two of these pieces. I can show you, I haven't got every detail here, but you could also show that they get updated separately. And is the domain logic clear? Yes. So before we had a Boolean flag, and now we have a choice. And what's interesting is that the ubiquitous language, the set of words that we use to talk about the domain, has evolved as we've done this process. Because originally we just had a contact, and everything was a string and a Boolean. And now we have things like, we have a concept called an email address, and we have a concept called a verified email address, and we have a concept called a personal name, and a concept called an email contact, and so on. These are the words that business would use. I mean, we've actually discovered something. Not only have we got a better design, but we've also got a design that actually reflects the terminology that the business would use when they're talking about this thing. So this is good. So we've actually killed two birds with one stone. Better design and a more accurate characterization of the model from a business point of view. And of course, this is all compilable code. This is not a Word document, and this is not a UML diagram. All right, let's do one more thing. Making illegal states unrepresentable. So sometime later, we decide to add an address. So as well as having an email, a contact could have an address, a postal address as well. Okay, fair enough. Now the business says, you know, we need a business rule. A contact must have an email address or a postal address. That sounds sensible. All right, so let's look at this design. Does this design meet the requirements? Right, it's like it's got these two fields, email and address. It's like, no, it doesn't, because remember what I said, everything is required. Unless you say it's optional, it's required. So this design says that the email and the address are both required fields. That's not what I said. I said I could be one or the other, right? All right, let's make them both optional. Well, that doesn't work either, because they could both be missing. And that doesn't meet the rule either. We said we need to have one or the other, right? But they can't both be missing. So how can we model this? Okay. There's a great phrase, make illegal states unrepresentable. So rather than saying, okay, well, they can't both be missing, but we'll put a unit test in, we'll put some validation in, we'll try and make sure that it never happens. It's like, no, don't do that. Try and make sure the design captures the business rule so it literally can't happen. You literally cannot write code that doesn't meet the business rule. Okay, how can we do that? Well, if you think about it, a contact must have an email or a postal address. What does that mean? Well, it means they either have an email address, or they have a postal address, or they have both. Okay, that's three possibilities. Those are the three possibilities, and the missing, both of them missing, is not a possibility. So there's three choices. How do we model something with three choices? Well, we've seen how to do this, right? We say, well, it's either an email only, or it's an address only, or it's both. So now we have a type that represents the three choices. And what's great about this is, like, the choice where they're both missing is not an available choice. It literally cannot happen. There's not, the code will not compile. It's just not there. Not only that, it also documents, it communicates. If I come across this code and I say, well, you know, what are the business rules around these things? It's like, well, yeah, you can either have one, or you can have the other, or you can have both. So it's a self-documenting code, which is very nice. And then we take this choice and we stick it in our contact. So the requirements are now encoded in the type system. We don't have to write unit tests, that's great. The code is also self-documenting, which is great. All right, so we can build this thing up. Now we've got yet another type, okay? We started with one type, now we have like 20 types. So the types really multiply. Luckily, they're all really short and they all fit on one page, so that's good. So before they were separate, and afterwards we've merged them into one type. All right, this is awesome. So static types for domain modeling, they're almost as awesome as a cat on a unicorn. Maybe not as quite as awesome, but I think they're pretty awesome. Let's do one more little tweak. Chances are the business doesn't really want that rule. That's what they said they wanted. As always, what they say they want is maybe not what they really want. And I go back to them and say, is that what you really want? It's like, actually, no. All we want is we have to have at least one way of being contacted. Okay, I don't care. First of all, it kind of looks kind of ugly. So we just say you have to have at least one way of being contacted. Fine. How do we model that? Well, we say, here's all different ways you can be contacted. You can be contacted by email. You can be contacted by postal address. We could add, you know, Twitter or Skype or something. Those are different ways of being contacted. And then when we have a contact, we have two fields. One is the primary contact info, and the second one is the secondary contact info. And it's very clear from this design that the primary one is a required field, and the secondary one is optional. So you have to have at least one way of being contacted, and you might have a second way of being contacted as well. It's not quite the same because you could have two email addresses, for example, so it's not exactly the same logic as the previous one. So let's look at what we covered. I talked about this challenge, right? Could we make that original design better? I talked about ubiquitous language. I talked about self-documenting designs. I talked about algebraic types and products and sums, and using choices to model things rather than inheritance. That's a kind of key takeaway. And then we talked about designing with types and using options instead of null, using these single case unions to wrap types, and making illegal states representable, trying to capture the domain rules in the type system directly. So that's a good time to stop there. I think there's a lot of things I can't cover right now. I could talk about state machines. That's a really interesting one. How do services work and blah, blah, blah. There's lots of stuff to talk about, but I'm not going to talk about it. Thank you, because it's the end of the day. So, okay. The slides and the video for this talk will be on my website, fsharpforfunandprofit.com/DDD. And in fact, they're already there because I've done this talk before. So if you want to see this talk again or you want to look at the slides, that's all there. If you want consulting, I have a business, F Sharp Works. If you want to know more about F Sharp, if you think that F Sharp is just awesome, go to fsharp.org. You can download it. It's a cross-platform language. It works on a Mac. It works on Linux. It works in Visual Studio, but it also works in VS Code. You don't need to have the whole Visual Studio thing if you don't want to. And you can also join the F Sharp Foundation for free and then participate in the Slack channel. And finally, I have a book coming out soon called Domain Modeling Made Functional. What a coincidence, the same title as this talk. So it's just it's in the early access, it's in the beta right now, it's not finished. You can buy it now if you like, if you're desperate to read it, or you can wait a couple of months and you can get it when it's finally ready. But I hope you will like it. It's basically this talk extended into a book. And I think that is it. So thanks very much. And of course, feel free to grab me, ask questions, whatever. And there's by the way, if you're interested in F Sharp, there's a functional lab every day at 1:40. It's in room 10. You have to go out towards the front and then go up some stairs. So if you want to see some demos of this, I can demo this stuff to you directly if you're interested. So definitely check out the functional lab. Cheers.